students, welcome to Sunil's tutorial. I'm Sunil Mirwani and today we will be doing this chapter called as ionic equilibria. Let's see the mechanism of a basic buffer. Let's try to understand the mechanism of basic buffer. Now what is a basic buffer? A basic buffer is a mixture of a weak base and a salt of a strong acid. A basic buffer is a mixture of weak base and salt of strong acid. Right? Now, for example, let us consider ammonium hydroxide. That's my salt of, that's my weak base, and let's consider salt of strong acid, that is ammonium chloride. Right? Now, since the salt is a strong electrolyte, it will dissociate completely. Since the salt is a strong electrolyte, it will dissociate completely. Right? And the weak base will be slightly ionized, and the weak base will be slightly ionized. Right? Now, the degree of dissociation of ammonium hydroxide is going to be reduced due to the common ion ammonia. The degree of dissociation of ammonium hydroxide is reduced due to the common ion. Common ion ammonia due to the ammonium ions. Now, the ionization can be represented as ammonium hydroxide ionizes incompletely to give you ammonium ions and hydroxyl ions. This is your weak base. Right? Similarly, ammonium chloride, salt of strong acid, will dissociate completely to give you ammonium ions plus chloride ions. Right? The ammonium ions formed by this salt of strong acid are going to suppress the degree of dissociation of the weak base. Now, case 1. When small amount of strong acid is added to the buffer. If small amount of strong acid is added to the buffer, then the ammonium hydroxide molecules will get neutralized. This acid will combine with ammonium hydroxide to get neutralized. Acid base combine with each other to form salt water. You already have a base in there, you are adding an acid will combine with base for neutralization. It will get neutralized, hence the pH of the solution will remain constant. pH of solution remains constant. For example, ammonium hydroxide combines with the acid, neutralization reaction takes place. Neutralization reaction takes place to form ammonium ions plus water. This is your base, combines with added acid, right, to give you water. Now this capacity of the buffer solution to resist change in pH even when a strong acid is added to it is called as reverse basicity. We've done this with mechanism of acidic buffer also. So I can say that the capacity of buffer solution, which resists the change in pH, even on addition of strong acid, is called reverse basicity. Right? This was when a small amount of acid is added to the solution. What happens if a small amount of base is added to the solution? Case 2. When small amount of strong base is added to the buffer solution. Now when a small amount of base is added to the buffer solution, the added hydroxyl ions will combine with the ammonium ions and will get neutralized. You already have excess positively charged ammonium ions in the solution. Because of common ion effect, there are excess ammonium ions. These excess ammonium ions will combine with the added hydroxyl ions to get neutralized, right? The added hydroxyl ions will combine with ammonium ions and get neutralized to form unionized ammonium hydroxide, right? Hence the pH of the solution remains constant. The pH of the solution remains constant, right? That means I have ammonium ions reacts with hydroxyl ions to form neutralization ammonium hydroxide, right? This is your added base, this is neutralization, right? So here, that's the reason why even when I add a base, the pH does not change. And this capacity of the basic buffer solution to resist a change in its pH when a strong base is added to it is reverse acidity. The capacity of buffer solution to resist change in its pH on addition of strong base is called reverse acidity, right? So that is your reverse basicity and reverse acidity, right? So do you understand the mechanism of a basic buffer? That's the reason why the pH of the basic buffer does not change. Next, let's see what are the properties of a buffer solution. Properties of a buffer solution. Properties of a buffer solution. 1. The buffer solution has a constant pH value. It has constant pH value. Next, the pH of the solutions remains constant even when small quantity of strong acid or strong base is added to it. The pH remains constant when small quantity of strong acid or strong base is added to it. Strong acid or strong base added. Right? Next, the pH does not change even on dilution. pH does not change on dilution. Right? And the pH does not change even if the solution is kept for a long time. pH does not change even if the solution is kept for a long time. Right? Those are your properties of buffer solution. Where do I use buffer solutions? Application of buffer solutions. Where do I use buffer solutions? Right? First, buffer solutions, they are used to preserve, solutions are preserved in the presence of buffer solution for a long time because they resist any change in pH. So I can say that first, solutions are preserved in the presence of buffer solutions. Right? Next, penicillin preparations are preserved and stabilized by using sodium citrate buffer. Penicillin preparations are preserved and stabilized by sodium citrate buffer. Next, sodium benzonate is used as a buffer to preserve jams and jellies. Sodium benzonate is used as a buffer to preserve jams and jellies. Right? And you could also say that to control the change and pH of the soil in agriculture, buffers are used. To control and change pH of soil in agriculture, buffers are used. Right? Those are your applications of buffers. Fine, do we understand this? Next, let's move on to something else. Let's see what you mean by solubility product. What do you understand by solubility product? What do we understand by solubility product? Now, when any ionic compound is dissolved in water, it dissociates into cations and anions. As the concentration of ions in the solution increases, they collide with each other and reform the original solid. This dynamic equilibrium that is established between the solids and the ions in the solution is called as, thus a dynamic equilibrium is established. I can say the types of solid where you have which are slightly soluble in water are called as sparingly soluble solids. Now these solids, if they are shaken in water, in little quantity of water, they form dilute saturated solution, and this dilute saturated solution is called as your solubility. Then to what extent will they dissolve in water will be the solubility. So how do I define solubility product? Solubility product at equilibrium, the product of the concentration of the ions at equilibrium, the product of the concentration of the ions, the product of the concentration of the ions of sparingly soluble salt in its saturated solution is constant. The number of ions do not change, is constant at a given temperature and is called as and is known as solubility product. So what do you understand by solubility product? If you have a salt which does not dissolve in water very easily, if you put it in water, shake it, it will dissolve to some extent to form a saturated solution. That saturated solution will have some ions. The product of those ions is called as your solubility product. Fine, do we get this thing here? In that case, how do I define solubility? How do I define solubility? Solubility, the maximum concentration of a substance in a saturated solution is known as its solubility. What will be the maximum number of ions that will be present in a solution at a given temperature is its solubility. Right? The maximum concentration, of a substance, the maximum concentration of a substance in its saturated solution is known as its solubility, right, at that given temperature. Fine. Now it is expressed in moles per decimeter cube. It is expressed in moles per decimeter cube. Fine. So now that we know what is solubility product and solubility, let us try to find out an expression for solubility product. Expression for solubility product. Let's try to find out an expression for solubility product. Let us consider BA is a salt which is sparingly soluble in water. BA, let BA be a sparingly soluble salt shaken in water. Right? Now, a very small amount of salt will goes into solution form to form a saturated solution because this is a sparingly soluble salt. Right? So, a very small amount of salt goes into solution to form a saturated solution, right? While most of them remains undissolved, the ionic equilibria of this sparingly soluble salt Ba can be written as the ionic equilibria of this sparingly soluble salt Ba can be written as Ba will be a solid unionized will ionize reversibly to form B plus aqueous ion plus A minus aqueous ions. Right? These will be the ions present in the solution. Right? Now, if I apply law of mass action to this, apply law of mass action, I can therefore say that equilibrium constant is going to be active mass of B plus into active mass of A minus upon active mass of Ba. Right? So in which case I can say that K into active mass of Ba is going to be nothing but active mass of B plus, which is in aqueous state, into active mass of A minus, which is in aqueous state. Right? But as the solution is already saturated, this is a sparingly soluble salt, I've shaken it and the solution is already saturated, the concentration of unionized Ba molecules will therefore not change. Right? As the solution is saturated, the concentration of unionized Ba will be constant. Therefore, I can say that K into constant is going to be active mass of B plus aqueous into active mass of A minus aqueous. Right? Now this K into constant can be written as KSP, or this can be called as your solubility constant. This is your KSP. So KSP is active mass of B plus into active mass of A minus in aqueous state. Right? That is your solubility product. Where KSP is called as a solubility product of a sparingly soluble salt. Where KSP is the solubility product of sparingly soluble salt. Sparingly soluble salt. Fine, we get this in here. This is your expression for solubility product. Now, let us try to derive expression for different types of equation. Right? Let us try to find out expression for solubility and solubility product for a Ba salt. Expression for solubility and solubility product for salt of Ba type. Right, let's take up different types of salt and let's do this. Right? Now, I want to find out the expression for solubility and solubility product for a Ba type of salt. It's not same as your previous derivation. There I just defined what is solubility product. Now I'm going to use that and derive something else. I'll just show it to you. Right? So let us consider that. Let us consider that you have a sparingly soluble salt Ba shaken in water. Let Ba be sparingly soluble salt shaken in water. right? If it is a salt shaken in water, let us assume that S is the solubility of the electrolyte and Ksp is the solubility product. Let S be the solubility of the electrolyte and Ksp be the solubility product. Right? In which case I can say Ba will dissociate reversibility to give you B plus ions and A minus ion. Right? Now the solubility of this is S. The solubility of salt I have taken as S. Therefore, since you have same number of ions, if S is the solubility here, if it dissociates, a saturated solution will give you S number of B plus ions and S number of A minus ion. Therefore, my solubility product is active mass of B plus into active mass of A minus. Therefore, solubility product Ksp is going to be S into S. So Ksp is going to be S square. So the solubility product, here we are deriving an expression for solubility and solubility product. The previous one was an expression for solubility product. Here we are trying to find out the relationship between solubility and solubility product. Fine, do you get this thing here? Thus, I can say that if I rearrange this, solubility for a Ba salt is square root of its solubility product. Fine. This was a Ba type of salt. Next, let's consider another kind of salt. Let's consider a salt of type Ba2. Salt of Ba2 type. Right? Same assumptions again. Right? Let Ba2 be a sparingly soluble salt shaken in water. Right? So in that case I can say that its expression will be Ba2 when it is shaken in water. It will give you a saturated solution with B. If it is Ba2, that means the valency of B must have been plus 2A minus. Right? Now if the solubility of Ba2 is S, since I am getting one molecule of B, therefore its solubility will be S. Since I am getting two molecules of A, its solubility will be 2S. Right? So in that case I can say, but we know that solubility product is nothing but the active mass of B plus ions into active mass of A minus ions. Right? Now I can say that this is going to be solubility product. Active mass of B plus is S. Active mass of A minus is 2S. And here, since this is Ba2 type of salt, this will be A minus the whole square. There are two atoms of A here. So this is going to be minus A the whole square. So this will be S into 2S the whole square. So S into 4S square. So this is going to be 4S cube. So the solubility product of a Ba2 type salt is going to be nothing but 4S cube. Therefore I can say that S cube is Ksp upon 4. Therefore solubility of such a salt will be cube root of Ksp upon 4. Right? That is going to be my solubility for a Ba2 type salt. Right? Let's consider a Ba3 type salt. Salt of Ba3 type. Right? Let us consider that let Ba3, same assumptions again. Let Ba3 be a sparingly soluble salt shaken in water. Right? So in that case I'll get Ba3 it will dissociate to give you B plus 3, valency of B will be plus 3 plus 3A minus, right? If I consider the solubility of BA3 as S, then the solubility of B will be S and this will be 3S, right? Since this is BA3, the solubility product is going to be active mass of B plus 3 into active mass of A minus 3, so Q, right? So therefore I can say that KSP is going to be S into 3S the whole cube. KSP is going to be nothing but 27 S raised to 4. So the solubility product of a KSP 3 types of for a BA3 type of salt is going to be 27 S raised to 4. Therefore I can say S raised to 4 is KSP upon 27. S is 4th root of KSP upon 27. Right? Let's consider a salt of type now this should be very easy by now, BA4. Same derivation, right? I can say that let BA4 be a sparingly soluble salt. Soluble salt shaken in water. Right, so I'll get BA4 will dissociate to give you B plus 4 plus 4A minus. Right? If I consider the solubility is S, then this will be S and this will be 4S. But here KSP is going to be active mass of B plus and I have 4 atoms of A minus. So this will be A minus raised to 4. So this is going to be KSP is going to be S into 4S the whole raised to 4. S 4 4s are 16, 16 4s are 64, 256. 256 S raised to 4. So this is 256 S raised to 5. Right? So the solubility product is going to be 256 S raised to 5. Therefore S raised to 5 is going to be KSP upon 256. Therefore S is 5th root of KSP upon 256. Right? That is the salt of BA4 type. Now let us consider a salt of BA2A3. Salt of B2A3 type. This should be interesting. Right? Let's start. Let B2A3 be a sparingly soluble salt shaken in water. So in that case I can say that B2A3 is going to give you, the valency of this has to be, valency of B will be plus 3 and there will be 2 molecules of this, plus this is going to be minus 2 and there will be 3 molecules of this. Right? So in that case, if the solubility of this is S, this will be 2S and this will be 3S. Right? And but solubility product will be nothing but B plus 3 the whole square into A minus 2 the whole raised to Q. Right? So therefore I can say that the solubility product is going to be 2S the whole square into 3S the whole cube. So KSP is 4S square into 27S cube. So you will get your KSP as 108S5. Therefore S5 is Ksp upon 108. Therefore, S is fifth root of Ksp upon 108. Right? Now, I'm very sure by now you should be able to get the solubility product of any type of salt. Next. What do you understand by a saturated solution? We did 7th, 8th. Saturated solution. Right? Now, a saturated solution is a solution in which the solubility product is equal to the ionic product. Any solution in which the solubility product is equal to ionic product is called as a saturated solution. Solution in which saturated product is equal to the ionic product. Right? So any solution in which the saturated product Ksp is equal to the ionic product, that is B plus into A minus, is called as a saturated solution. Right? In that case, what is an unsaturated solution? What is an unsaturated solution? A solution in which the ionic product is less than the solubility product is called as an unsaturated solution. Solution in which the ionic product, that is B plus into A minus, is less than the solubility product. Solution in which the saturated product should be solubility product is less than the solubility product. So if they are equal, then it's a saturated solution. If the ionic product is less, then it is an unsaturated solution. In that case, what is a precipitate? Precipitate. How do I define a precipitate? A precipitate, a solution in which the ionic product exceeds the solubility product, is called as a supersaturated solution, and that excess ions are remain back, and that is what is called as your precipitate. Right? So a solution in which the solubility ionic product is greater than the solubility product. Ionic product is greater than the solubility product is called as a supersaturated solution. Is supersaturated solution, and throughout the excess salt present in the solid takes a form. That means the excess of the salt present in the solid forms a precipitate. Right? That's how you define a saturated solution, unsaturated solution, and a precipitate on the basis of solubility product. Next, let's see the applications of solubility product. Application of solubility product. What are the applications of a solubility product? Right? First, since we have defined this, the first application is in precipitation, in prediction of precipitate, right? If the ionic product is more than the solubility product, then before the reaction only you can predict what will be the precipitate and how much precipitate will be formed, right? That is the first application of solubility product. Precipitation of salt occurs, we can say precipitation of salt occurs when the ionic product is greater than the solubility product right. Thus, by knowing the solubility product of a sparingly soluble salt, it is possible to predict whether precipitation will occur or no, right? Thus, by knowing the solubility product of a sparingly soluble salt, it is possible to predict if precipitation will occur or not. Right? That's my first application of solubility product in prediction of precipitate. Or you will be able to predict whether you will have precipitation or not. Second, in qualitative analysis of basic radical. Analysis of basic radical. Qualitative analysis of basic radical. To separate basic radical into groups by precipitation, the principle of solubility product is used. Right? You have basic radicals, you can separate them into various groups. Right? First, I can have group 2 radicals. How do I get group 2 radicals? By using HCl. You must have done this experiment in lab. Qualitative analysis of basic radical. Right? First, you have use of HCl to separate sulfides of group 2. Right? For example, by passing hydrogen sulfide gas, the original solution through an original solution in the presence of HCl, only the sulfide cations are precipitated. When you pass by passing hydrogen sulfide gas through original solutions in the presence of HCl, only the sulfide group 2 cations get precipitated. Only sulfide group 2 ions get precipitated. Right? Do we get this here? So, and the group 3 ions are not precipitated. This is because only group 2 ions will get precipitated. The sulfides of group 3 will not get precipitated because the solubility product of sulfides of group 2 is less than the solubility product of sulfides of group 3. Group 2 ions will get precipitated and not group 3 ions because the solubility product of group 2 ions is less than the solubility product solubility product of group 3 ions. Right? And as they get precipitated, you will have, this is how you find out solubility, right? then this is how you precipitate group 2. Now suppose if I want to precipitate group 3 ions, in that case what should I use? What have you all used in that? To precipitate group 3 ions, you have to use ammonium hydroxide, right? Use of ammonium hydroxide to precipitate group 3 ions, right? That's the other application of solubility product, right? By passing hydrogen sulfide gas in the presence of ammonium hydroxide, only the group 3 cations get precipitated. By passing hydrogen sulfide gas in the presence of ammonium hydroxide, right? By passing hydrogen sulfide gas in the presence of ammonium hydroxide, only sulfides of group 3 ions get precipitated. Right? This is that also in this case only group 3b. If I use ammonium hydroxide, only group 3b ions will get precipitated. Suppose if I want group 3a ions, then I should use ammonium chloride instead of ammonium hydroxide. If ammonium chloride is used instead of ammonium hydroxide, then group 3a ions get precipitated. Right? So that's your application of solubility product. Right? We will stop this here for the day. Thank you very much.